Hi, my name is Aurélien Madouas. I am an associate professor in veterinary epidemiology at the Veterinary School of Nantes in France. And today I would like to show you how to use the STOCfree model, which is a model, a statistical model that we developed as part of a European project called STOCfree, which was funded by EFSA. So if you want to know more about this project, please visit this page, so stockfree.eu, and you will have all the project context and objectives and also the people involved. So regarding the model in itself, a full description and application were published in a journal called the Peer Community Journal in 2022. So if you want to understand all the modeling hypotheses, have a look at this paper. So I will just say a few words about the main hypothesis of the model that you can find in the article. So really, the point of the model is to predict the probability that a given herd is infected by some pathogens. So in our applications, we used infection by the bovine viral diarrhea virus in cattle. And so, yeah, we're interested in the probability that a given herd is infected at some point in time. The model outcome is a latent status, so is the infection present or not? And it's not directly observed, so that's why it's latent. And the observations we have to estimate the probability that it's present are test results that are usually performed as part of control programs. And sometimes we also have risk factors that can inform about the probability that the disease has been introduced. So the model works like this. So the time is discretized into months, and historical data are used to train the model, so to estimate model parameters. And the probability of infection on the last month of surveillance is predicted from all the evidence available up to the time of prediction. So to say a bit more about this, so the latent status is modeled as having a dynamic. So a probability of transition between infection and not being infected between consecutive months. And this disease dynamic is modeled using three parameters. So we have a first parameter that describes the probability of moving from uninfected to infected between consecutive months. And here there are two possibilities. So you can become infected with a probability tau1, or remain uninfected with a probability 1 minus tau1. And when you're infected, you have a certain probability of remaining infected that we call tau2, or a probability of clearing the infection that's 1 minus tau2. And for the first month of data, for which we do not have any prior information, we set an initial probability of infection that we called pi1. So when further to that, when we have risk factors, we chose to model the probability of new infection as a function of these risk factors using logistic regression. And so the other important part of the model is how is the latent status linked to the test results. And this is done normally, so using sensitivity and specificity. So basically, the sensitivity is the probability of having a positive test result when your latent status is infected. And the specificity is the probability of getting a negative test result when you are not infected. So in order to estimate the different model parameters and perform the predictions, we work in a Bayesian framework. And so we implemented the model in two different computer programs. So there was a first implementation in a computer program called JAGS, and we later on implemented the model in another program called STAN that we found to work better for the estimation. So we have put all the functions that are necessary to do the analysis in an R package, and you can install this R package from a website called GitHub. And so if you visit the GitHub page of the package, you will have access to all the code so which is contained in this R folder. So each file contains some function or steps necessary for the analysis. And you will also have access to what is called a README file, which contains a description of the main features of the package, and also steps on describing how to use the model. So what I'm going to do now is to guide you through this README file. So if you want to follow the different steps, I'm going through them. What you can do is to copy this file and execute it on your own computer. Here is the README file open in RStudio on my computer. So what I'm going to do now is to go through the most important steps that are needed for you to run the model. So first, to install the package, you will need first to install Stan. So and the particular version of Stan you need to install is called CMD Stan. And in order to install this, you just have to visit this page and follow the instructions, it's usually fairly easy. And you also may have to install JAGs. Then once you have all the necessary programs, the STOCfree package can be installed easily from GitHub, so using the install GitHub function, which is available from the remotes package. So if this package is not already installed on your machine, just install it using this instruction. Now, once the STOCfree package is installed, you just need to attach it by running by calling the library. So just like this. And if you need if you want to see the different functions that are available in the package, just run the call the help page, and you can see all the different functions that are available in the package. Also, I'm going to attach the ggplot2 package because we are going to make some plots later on. So, how is the analysis performed with this package? So what you will need to do is set up the test data. So the model needs some test results in order to determine the status of a given herd. So once you've set up the test data, because we're working in a Bayesian framework, you need to provide prior distributions for some of the model parameters. So there are prior distributions for both test characteristics and other dynamics parameters, so tau1, tau2, pi1, or parameters related to risk factors. So when you have risk factors, you also need to define priors for these risk factors. So when your model is set up, so with both test results, prior distributions, risk factors when you have them, you can then run the model and analyze the model outputs. So the package contains a toy dataset called herdBTM that we're going to use to show how it works. And so herdBTM is so it's herd level data, and the data we have are tests performed on bulk tank milk, so which explains the BTM. So the data you need to provide need to be at the herd level, so farm level, and you need at most one test per month, but it can be less. And also what you need to provide is a column for test results. So here we can have positive or negative test results. And also sometimes when you have multiple tests, you can also tell which are the tests used. So here we have two tests, so BTM, ODR, and confirmatory tests. So this dataset, we're going to use it as input for this function, so the STOCfree data, And this function is going to create so it's a stock-free data object that is going to be used by our model. So how does it work? So this stock-free data object, so you need to provide the name of a data set that contains the test results, so the herd BTM that we just discussed. And in this data set, you need to tell the function where is the column that contains the herd IDs, the column that contains the date of test, the column that contains the test results, and when you have multiple tests, you also need to say where is the column that contains the name of the test used. And further to that, there is the possibility to model the infection dynamics either on the probability scale, so between 0 and 1, or on the logit scale. So in what follows, I'm going to use the logit scale. So they can do the same, but it's just it changes the way you specify the priors, which is not really important. So I will use the logit scale because it's easier to follow. So I'm going to run this code and see what it gives in the console. So I have created this object, so sfd1, which contains so my test data, and so the function has created a new object, so I can show you what it looks like. So it's a list that contains different tables that are going to be used by my JAGS model or my STAN model. So you can, by running the str function on this object, you can explore the different bits of data that are in there. And so these objects have a class that will be used later on to determine the type of model that is used. So next we need to specify prior distributions for test characteristics. So here we have two tests, BTM ODR and confirmatory test, and we are going to specify priors using beta distributions. And these beta distributions take two parameters that will determine the shape of the distribution. So in this example, I've used beta 5260 for the sensitivity of the BTM ODR test, and beta 22 for the specificity. And for the confirmatory test, I've used parameter 22 for the sensitivity and 10,001 for the specificity. And so we can plot these priors to see what they look like. And so you can see that the BTM ODR sensitivity is pretty narrow, and specificity is wider. While for the confirmatory testing, we are going to assume that we know less about the sensitivity, but the specificity is extremely high, so we have no false positive. In order to help to specify these priors, we could also have used a function from this package that we developed as part of the project. So if you go to this page and install this package, you can you will be able to use a Shiny app to select the parameters of your beta distributions, which can be very helpful when you're not sure about which value to use precisely. So next we provide prior distributions for the parameters related to status dynamics. Earlier we said the model would run on the logit scale. So I'm going to jump directly to this section. So we have for the infection dynamics, we have three parameters. So pi1, which is the probability of being infected on the first surveillance month, tau1, which is the probability of becoming infected between months, and tau2, which is the probability of remaining infected between 2 months. So I'm going to provide prior so the values for the prior distributions. And here, yeah, I will put these values, which will result in these prior distributions. So the yeah, prior for probability of infection is yeah, really weakly informative, so it doesn't tell much about what is this probability. So using yeah a mean of 0 and a standard deviation of 1.5. For the probability of new infection, I'm going to say that it's yeah fairly low, probably below 20%, although it's unlikely to be 0. And for the probability of remaining infected, I'm going to assume it's fairly high, meaning that when you're infected, you're very unlikely to cure the disease between consecutive months. So these are the priors for the status dynamics. So if we had specified these priors on the probability scale, we could have done the same, but yeah, using beta distributions. So we could have obtained the same shapes, but it's a different way to parameterize it, which maybe is less intuitive because with the logit scale you have means and variances, which help you to see how yeah the scale and how wide are these distributions. So now our model is set up, and we can run it. So here is a recap of what we've done so far. So we've created a STOCfree data object from the herd BTM dataset. Then we've set up the priors for the test characteristics for the two tests and for the infection dynamics. So we're now ready to run the model, so which I'm going to do now. So I'm just calling the STAN model on the STOCfree data object. It is now complete, and you can see that so R calls a STAN to run the model, which is going to estimate posterior distributions for all our model parameters, and is also going to predict the probabilities of infection for all herds in the dataset on the last time point in the data. So let's wait to see what it returns. So Stan has finished to run, so it's done what we've asked. So we had 3 chains, and for each chain we got 1,000 iterations that are kept for analysis, and before that we had 1,000 iterations of warm-up that have been discarded that have not been saved. So this was pretty fast for this small data set. And so now we can look at the output. So in the output there are two components. So there are the model parameters, so related to both disease dynamics and test characteristics. And one way to get these parameters is to extract them from the model we've created. And another way is, if we've saved the parameters on the disk, is to read them back from the disk. So here the out path is going to be the out path you've specified here in the call to STOCfree stan. So here. So if we look at these parameters, so we can choose the first way. So this will read the model parameters. So we can see what are these parameters. So we had 2 tests, so 2 sensitivities, 2 specificities, 1 parameter for new infections and 1 for the probability of remaining infected for 3 chains, and so 1,000 iterations per chain. So we can look at different summaries. So we can have trace plots. So here for the first sensitivity. We can do the same for the second sensitivity. Okay, so everything looks alright. The chains are mixing well. And we can also look at density plots. to see what's the posterior distribution for each parameter. So again, we can check any parameter we would like. And also you can get so a summary for each parameter. So posterior mean, posterior standard deviation, median, and different percentiles. So this is the first part of the output, and the second part is the predicted probability predicted probabilities of infection for each herd in the dataset on the last month of surveillance. So again, you can either extract these probabilities from the stand object or read them back from the disk. So I'm going to extract them from the stand object, and again you can plot these probabilities for all the dataset or for herds that you're interested in. So here I've plotted the predicted probabilities of infection for the herd FR001 or FR002, and you can see that they have different predicted probabilities of infection. And as for the parameters, you can display summaries for these probabilities of infection. So there could be many variables that could predict the occurrence of a new infection, and you may not know them in advance. And this can be really hard to test with a Bayesian inference done with using MCMC. It can take a lot of time. So in order to help you to identify the best predictors, we've included in the package the possibility to evaluate these risk factors using GLMs. So to test that, there is a small dataset, a small toy dataset in the package called Intro, and this dataset contains a number of cattle introduced in each of the herd for which we have test results. And so each row of data is farm ID, a date of introduction, and a number of cattle introduced. So the README page describes how to perform this evaluation using this test dataset and various functions that are in the package. So all these functions use the GLM function from the base R, and you can evaluate lagged relationships and plot them using cross-correlation maps. But I'm not going to go into too much detail about this as it would take too much time, and you can try out what is in the README file, and feel free to send me questions if needed. And so once you have identified the best risk factor, or best risk factors, you can include several of them. You need to add them to your STOCfree data object. So there is a function called add risk factor to a STOCfree data. So you need to specify the STOCfree data object you've created before, as we did in the first part of this video. Then the risk factor data that in which you have your different risk factors. The name of the farm ID, so that the function can link the farm ID in the test dataset to the farm ID in the risk factor dataset. The name of the risk factor, of the column containing the risk factor, here, the date associated with each risk factor, the type of risk factor, so which is it's either continuous or categorical, and if there is any lag, the lag between the occurrence of the risk factor and the likely new infection. And once you've done that, you also, as before, need to provide prior distributions for the association with the risk factor. So here we have one risk factor, so we need which is continuous, so we need to provide a prior distribution for the intercept of the logistic regression. and another prior distribution for the risk factor. So in the this would be equivalent to so this will replace the prior for tau1 that we specified in the previous part. And once this is done, you just run the model as before. So you can add priors for the different tests, prior for disease dynamics, and running the model is exactly as we did before. So that's the same function. You give a STOCfree object as an argument, and it detects that there is a risk factor present, and the model runs just as before, and the output is analyzed in the same way. Okay, so I'm not going to tell more about this. So this is the end of this tutorial. So I hope it was helpful and that it will help you to use this model. And if you have any question, feel free to contact me.